Okay, so thanks to the Math Club leadership for this very, very kind invitation. So I was so sad that it was not possible to come to Kunshan and give a class and meet all of you. And now reading all these names of my dear students, it is even harder than before. But still, I'm really happy that we have this connection. And I would like to give a talk today about the arrow of time. And before I give the talk, I would like to say a few words about the topic, why I selected this topic, and why this is a good topic to give a talk now at the Math Club. And the point is, first of all, it's a very interesting question, which is very important from the mathematical, philosophical, physical point of view, and has many interesting features in all these sides. So in the idea of connecting different subjects, which DKU embraces, this talk fits very well. Another reason is that I would like to give you some connections to actual research being done. I think as students, you might be interested in research topics, things which are going on really at the time. And there's a few things which are related to this arrow of time, few new insights which I want to tell you about. And I also try to connect to research I'm doing, which is a little bit on the side of the topic, but I would like to tell you a few things about ideas and thoughts which are related to this arrow of time topic, which have to do with the research that is being done. This I do for two reasons. First of all, I think it's always nice for students to have these connections and to understand and see that what you're doing is not so extremely far away from research topics. That's one thing. And the other thing is also to make it clear to you that there's this connection, right? The DKU still doesn't have master programs. I hope this is going to happen soon. But to be aware that you have been taught by faculty who are in Duke, for example, or as in my case, now in Munich, later in Tübingen, who do interesting research and where you can have connections in the future, and that you really have the prospect to do very interesting research when you graduate, right? Before I tell about the arrow of time and give you the details, what it means, I would like to talk about one of my heroes. You know, everybody has his heroes, and for some of you who like physics, it might be Einstein, or I don't know, Newton, all kinds of scientists. And one of the most important physicists ever, or mathematical physicists, was Ludwig Boltzmann. Just a few words on Ludwig Boltzmann. He was from Austria, and he was a physicist and philosopher. I would say very on the rigorous side. So today he might be a mathematical physicist. He was born in Vienna, Wien, in Austrian or German language, in 1844. And he died in 1906 in Trieste, which is today in Italy. At that time was part of Austria. The story of his death is kind of sad. He committed suicide at this time, so he was depressed. And in fact, it was that he was one of the most influential and important physicists of all times, and still his ideas were not recognized when he was alive. So he was ridiculed by some of his colleagues. Nobody, only a few really understood, among others Maxwell, how important and interesting it is what he does. And he had a kind of a sad life and committed suicide, which had to do with his depression, of course, but also with the fact that he was ridiculed by his colleagues. And one of the things he was ridiculed for was this idea of atomism. So he had the crazy idea that gases and also liquids are not something which is continuous, but it's made out of atoms. And these atoms fly around, and with the laws of motions for atoms which might collide or not, he had the idea that the laws of the physics of gases can be explained and described. Nowadays, we all know that this is the right view, but at his time, people thought that was just crazy. And he had many opponents, for example, Mach or Max Planck, who thought that this is just nonsense. Now, let's come to his ideas about the gas laws. And at that time, when Boltzmann lived, gases usually were described by so-called macroscopic values. Microscopic values, for example, the density rho of the gas, the volume V of the gas, the pressure of the gas, the temperature. And there were certain laws which described how these gases behaved. So there was this, I think in the English and American community, one usually calls this Boyle's law. In Europe, we usually say Boyle-Maillot, which says that the product of pressure P and the volume V of a gas is a constant sorry, here's a misprint, that's an at given temperature. So if you don't change the temperature of your gas and it's in a box and you change the volume, then of course the pressure changes. So if you decrease the volume, you get an increase of temperature. That's also something you see from empirics. So let me give an example. Assume you don't have enough air in the tire of your bike and you pump air into it. And you see that at the pump you heat up. So when you press the gas together, you have to work against it and the temperature increases. There's the law of Gay-Lussac, which says that if you keep the pressure fixed of a gas, the volume is inversely proportional to the temperature of the gas, which means that if you increase the volume at the same pressure, if you want to increase the volume and keep the pressure constant, you have to increase the temperature. So increasing the temperature, you know that gases tend to increase the volume if the pressure is fixed. Now, these were the gas laws which were known from the empirics and very well studied at Boltzmann times and many years before already. And now Boltzmann had the idea that you can give some atomistic explanation for these things. So his idea, if you have a box and you have a gas inside, this box is like many, many atoms. I've painted a few here. Now what happens is that eventually some of these atoms will hit the boundary of your wall and get reflected. And that's where the pressure comes from. You know that if you want to change your velocity, in this case, the x component here of the velocity, there has to be a force acting on these atoms. And this force here gives you a pressure to the boundary of this box. So for him, it was clear that by the pattern by the motion of these gas particles, that you can explain why there is something like a pressure on the wall. Now you can try to find out about these gas laws, which I told you, and that's really what Boltzmann did. Now he used this idea to derive these laws for the physics of the gases. And the density rho is given by is of course the number of atoms per unit volume. That's one of his ideas. So that density, if you have this atomistic idea, is related to the number of atoms per volume. This is rather obvious. Now the pressure is due to the kicks with the boundary, and the temperature is the energy of the particles. That was this idea that this makes sense to describe temperature as a kind of an energy. We will discuss this a little bit further later in this talk. Now let's assume that you have many, many atoms in this gas with all kinds of positional momenta, so a high disorder in the system. This is very important for this assumption, and this assumption will be very, very important for the rest of the talk. So we assume that there's a high disorder. Otherwise, if you know all these atoms sit at the same position and have the same velocity or momentum, and they hit the wall all at the same time, you don't have a pressure, which is something which typically stays rather constant in time. Now here we have this kind of assumption of chaos. Now, the higher the density, the more often particles hit the boundary, so the stronger the force. And the smaller the volume of this thing, the higher the density if you keep the number of atoms fixed. And this already gives you this law, P times V is constant. So increasing V, you have less of a density, then P also gets less, so and decreasing V, P increases and the product stays constant. Now, what's the second law I gave you? That is one of the laws I gave you. The second one was that if you decrease the volume of such a gas, that the temperature increases. How can this explain? Well, if you decrease the volume, you hit the atoms, right? So the velocity of these atoms gets larger. So if this wall, for example, moves to the left and one of the atoms hits, it's not reflected with the same velocity. No, the velocity is increased if this wall moves to the left, for example. So if this wall moves in such a way that the volume gets smaller, the velocities of these atoms hitting the wall increases. Now, the kinetic energy grows with this effect, and since temperature is proportional to the kinetic energy of the atoms, the temperature grows. I'm sorry, the temperature grows, and we have that in decreasing the volume, you increase the temperature. There's someone in the chat. Ah, okay. So if you want to ask questions, maybe you unmute, because I don't think I'm going to read the chat. Is that okay for everybody? Just interrupt me. That's fine. Okay.
Sure. Can I ask them?
Yes.
So basically, if he was opposed by so many scientists, what was their idea of gases?
Well, their idea was really that it's something continuous, that there's not atoms, that it's something continuous and is described by these kinds of laws. The point is, that's a very important question. The idea of physics, you know, physics started to appear in many different fields. And one of the big ideas of physics, which brought the most important impact, was the idea of universality. That has to do with the work of Newton and also with the work of Boltzmann. At Newton's time, for example, people had the idea that there's ballistics. You know, if you throw objects, then they have a certain law how they fly. And there was stellar dynamics, which was completely separate from ballistics. And there was laws how stars and planets move. And now one of the big ideas of Newton was to bring those together and have the idea that's the same physics, and to have a universal description of both. And that was one of the ideas which led him to the idea of the laws of gravity. And that was, of course, one of his most important insights. Here it's similar. Here people described particles which fly around and stars and ballistics, and had Newtonian laws of motions for these things. And they had a completely different description of liquids and gases. And the description came from empirics, and by experiments, they found out about all these laws, Gay-Lussac, Bohr-Mayotte, and they just described it and thought of a gas and liquid as being something continuous. Where if you look with more and more details, you always see something which still stays continuous. That was their idea. And I think universality is here something which was Boltzmann's insight, to say, okay, that these laws can be understood by different laws, which are then more universal. I think that was the ingenious part. And yeah, that's his findings. Okay, also to all the others, anytime, please interrupt. I think we are a small group and we can really have a discussion going on and have an active seminar. I think that's maybe the most profit. Now, there was this other law. I would like to not to go into detail too much about all these laws, and some of you have seen them already. When I came to Kunshan and gave a mock-up class, we did something like this already, and this is a little bit more giving you details. And the faster the particles are, of course, and if the kinetic energy is the temperature, so the higher the temperature, the faster the particles. And if this particle which hits the boundary is faster, of course, the force is stronger, and which means that the pressure increases, and you get these kinds of laws. So if you have some time, what you can do is you can really show that it's proportional. You could say, well, why is it P divided by T and not P squared over T and not the force or something? If you look at a little bit more at the details, and this is something you can try to do and ask me later in one of the next days how this is done, you can really show that it's proportional, and you get this proportionality here, this direct and this indirect proportionality here. Let me tell you a few things about the research. As I told you, I would like to say you that what research is done in my research group, which is related to that. And one of my most active research now, and this is very much related to this talk with the error of time, is about gases which have no boundary and which are very dilute gases. And if you have a very dilute gas, the system will be described by a Boltzmann equation. So without boundary, here I want to say that it's not in equilibrium. It's not in a box and has hit the balls many times and is in some equilibrium condition. It's less about the boundary, but more about equilibrium. And if it's dilute, you get the so-called Boltzmann equation. And this is a very interesting equation. For the following reason, and this will be important, as I said, for this talk. If you look at the equation itself, this law, which gives a law for the density of your gas, this is not reversible in time. So this equation has a direction, which makes it very important for the rest of this talk and for many also philosophical reasons. And I will come back to this Boltzmann equation later. This is one of my most active research to derive this Boltzmann equation from the microscopic picture. You could also, instead of gas particles, say, okay, let's look at other systems. For example, I have the idea of a galaxy. And a galaxy is made of many, many, many stars. And also this galaxy formed by these stars has its own law. And the law comes from the motion of the single stars. And there you can also try to find some macroscopic laws for the density of your galaxy, for example, coming from the microscopic motion of the stars, similar to this, right? Here I discussed the microscopic motion, how the atoms hit the boundary and what they do, and gave you laws for the macroscopic description, temperature, pressure, and so on. And this can also be done for other systems. Also for plasmas, and for plasmas it's very, very important for the following reason. You know that there's this big international project of this fusion reactor. So that was started as a European project, but now many other countries, also China, are involved in this tokamak fusion reactor, which has been built in France. And there one creates a very hot plasma, and this plasma is so hot that you have nuclear fusion going on in this plasma. What's a plasma? Well, a plasma is a combination of atoms and electrons. So if you heat up a substance such that the electrons which are in the outer shells of your atoms, if it's so hot that they really are all ionized, and you have some kind of a mixture of two gas-like things, an electron gas and a gas out of atoms, this is then a plasma. And this plasma also can be described as before, that you say, okay, you have equations of motion for the electrons and the atoms, and then you have some macroscopic equation of motion for the density of the plasma and things like this. And one of the most technological difficulties here with these reactors is really to understand how this plasma flies around and to keep it stable, that it doesn't hit the boundaries. And all these, and these plasmas are described by the Vlasov equation. There's very nice techniques I found a few years ago to build this bridge between the microscopic motion of stars or electrons and atoms and to the macroscopic description, law of motion for the density of the plasma, respectively the galaxy, which now give the strongest result when it comes to singular interaction. And you know that all interesting interaction here are singular. Gravitation has a Coulomb singularity, and also electromagnetic interaction has this Coulomb singularity. Well, to describe what it means to be singular in easy terms, well, if two stars get closer and closer, the interaction, the gravitational force gets stronger and stronger, and if these stars are described like point-like particles, it will tend to infinity if the distance goes to zero. The same is true for plasma, and older techniques didn't allow for singular interactions, and now there's new results And this is really something where there's a lot of activity in my research group, which might also give some room for later work together in kind of signature work. You could also look at electrodynamics, and this is something I will do on the next slide because it's also very, very interesting. And if you do electrodynamics, also, this is very German to have a K here instead of a C. I'm sorry for all misprints. So electrodynamics, and you get the Maxwell's equations. And there's also interesting research one can do with biological system. Also for biological system, there's, for example, slime molds, which have very interesting biological features. And these are colonies of amoebas, so many, many single amoebas doing very primitive stuff, each as a single object. And now if you look at the collective behavior of the colony of amoebas, similar as I just looked at the collective behavior of atoms to describe the physics of the gas, you get very interesting equations of motions which show very intelligent features and describe lots of the behavior. And what is interesting to see there is that the behavior of the individual is very primitive. So you could assume that by chance this was encoded in their DNA to behave like that, and that they start to make a behavior which then is for the colony very important and very interesting. If there's some time at the end of the talk, and if you like, I can explain you what's going on there. And there you see that sometimes already simple changes on the microscopic scale have some strong impact. And this is very important, I think, also for evolution theory. If you look about evolution, sometimes you might think, okay, well, there's so many things which have to happen and to go on to have an intelligent behavior for the individuum. And that it's a little bit strange that all these just by mutations, all these happens, and animals are formed in a way to work so perfectly. And these slime mold systems are some very simple system where you see that there's a very intelligent behavior coming out if you just do some very simple tuning of parameters for the microscopic system. And therefore, this is a very interesting research topic. All these are things done in my research group and many more. There's a lot about quantum gases and things like this. And I'm not just mentioning a few, which are very closely related to the topic today.
So basically,
yeah.
So this is basically the kind of research your group covers over there in Germany?
Yes. Yeah.
Oh,
it's just a fraction of it, just a part of it. There's a little bit more than this, but all these. So if you look at my research papers, this is very actual. I don't have a paper yet, but if you look at equation, Maxwell's equation, so I have many papers on the derivation of Lassifration for these systems here. And the focus is on interactions which have singularities. There's not many results on singular interaction, and most of them are rather weak. And there's quite a number of coming from me together with PhD students. There's a paper on deriving the Maxwell's equation from a so-called second quantized system. And I do not know of any other result where the Maxwell's equation are really derived with rigor from a second quantized system. So yeah.
So these are like PhD programs.
That was a PhD program, yes.
Oh yeah, all of them?
No, not really. There was one of them was done here. There was one part done with a master together, and then the follow-up done with a PhD student. That was together with a PhD student. That was also a PhD student. Yeah.
Okay, so most of them are PhD.
Well, that's hard to say. I also have master students working on programs like that all the time.
Okay. Also, Aya had a question in the chat.
Yes.
She's asking if you can come to DKU and give a talk on Vlasov. I was wondering.
Yes, I would like to. I can give a class Vlasov equation if you like this. I can, if you like.
Yeah.
So this talk today is not technical at all. It just gives you ideas and insight, and I can also show you a little bit more about the techniques. And the nice thing is, I think that the principal ideas of the techniques can can be explained to you, and we can discuss about these technical things. I'd love to.
Can we?
Yeah.
Can we talk about the biological systems one more depth also?
Yes, yes, of course, anytime. Maybe at the end of the talk, I can give you a few more pictures on what's happening there and why it's interesting.
Okay, okay.
And what I would like to give you 2 slides on is the electrodynamics and the Maxwell's equation, because I think this is also a very nice question. And just to give you the right picture. So assume you have some kind of antennas. Here you have a sender, some antenna which sends a radio signal. And here you have some receiver of the signal. And then you typically describe what happens in between by solving Maxwell's equation. Well, this is one example. There's other electrodynamical effects where Maxwell's equation play a role. This is one example. And now this, if you know that quantization tells you, quantum mechanics tells you that also electromagnetic interaction have to be quantized, and that these waves, these electromagnetic waves here have to be described by photons, which means that in a quantized description of the system, which is more microscopic, so to say, you have here this sender emits photons, and these photons fly around. And now the point is to show that now when these photons hit the receiver, they interact with the electrons in the receiver, and to show that this interaction is just like the same as it's described with the Maxwell equation. So this is very similar to what I did before, right? If I say, okay, I have a gas, it has certain gas laws, for example, Boy-Maillot, Gay-Lussac. That's some kind of laws, and it behaves like that. And if you do something in the gas, for example, increase the density, then you have a wave running through, and that has an effect, and all this. This is a description. Now, if you understand all these gas laws from the microscopic picture from atoms flying around, you have a more microscopic, more fundamental description of what's going on. And of course, at the end of the day, it has to explain what happens, and both explanations should match. And the same is true for this system of sender and receiver, for example. You describe it in the Maxwell equations way, or you can do the quantization of the photons and get the same result. And this is something which has also been done in one of the papers I did with my PhD student. It will be published now. So we just get the positive results from referees. So it will be in a journal very soon. And I think it's nice to also have this picture. The reason I'm giving is that this idea, this principal idea of Boltzmann is not solemnly going on with gas laws. You see this in all kinds of physical, biological, in all kinds of systems. You have behaviors like that you have a microscopic description of many particles, and this gives you some macroscopic laws. Now, so far what I discussed didn't have so much to do with the error of time, just a little bit, because I told you about this Boltzmann equation, and there I said something which might be very surprising if you are confronted with it for the first time. And it is the statement that this Boltzmann equation now is derived from the Newtonian dynamics of many gas particles. And the point is now the Boltzmann equation itself is not reversible in time. And that's a little bit surprising. Because the equations of motion on the micro level we had, in this case Newton, has no preferred direction of time. But the macroscopic world does, and the question is, how can that be? To emphasize this point, I'm sorry, I wanted to show you a video to emphasize this point, because I think videos is something you can take home with. Now, if you look at the system, you have a system of many particles. This is described maybe by quantum mechanics, Schrödinger equation, which doesn't know a direction of time. And if I show you this video, you will be able to say that there is eventually a direction of time. And everybody of you might agree that what I did was some kind of a cheating. I showed you a video of a system and played it backwards. So being able to distinguish between backward and forward direction tells us that there is an error of time. On the microscopic level, there isn't. So if you look at all the atoms building this kind of a glass and their equations of motions, they do not have a direction of time, but the full system does. How can that be? I would like to give you a simple model where you have a direction of time on the macroscopic level, but not on the microscopic level. And this will be very important, a very important explanation. This explanation also goes back to Boltzmann. Just a few words on Boltzmann. Well, he had not only that he had this ingenious idea to describe the laws of gases from this atomistic point of view, in a time where people just had a completely different picture of it, right? It was some kind of revolutionary idea. And of course, it's always hard if you are used to a certain picture, which everybody has to make this very different. Now, not only that he has had these ingenious insights and ideas and could give you the connection between these two things. Now, what he did was so much. So he was attacked by many people and he always had the right answers and had the right ideas, how to describe the direction of time, what works, what doesn't work. So it's really very, very impressive what he did in these few years. And now some model which goes back to Boltzmann in some sense, maybe not with these details, but the rough ideas for sure is that you have now this a kind of a box. In the box you have a wall and there's a small hole in the wall, a very small one. And you have gas on the right side of the box. Now, the very important point is that the particles are all on this side. Now what happens, they fly around according to Newtonian's equation of motions and eventually a particle will go to the other box. And if you wait for a long time and the behavior is rather chaotic, at the end there will be many particles here and many particles there. Now for this simple model, gas goes from the right to the left. So there is some kind of special behavior, some direction of time. The system is macroscopically irreversible. So it will not happen that all the particles here will at the same time go back, or not in the time frame which you will encounter. This is a very important thing we shall discuss later in this talks. So this is explained by the natural motion of the atoms. And you see that this explanation has a lot to do with the initial condition of the system. And that's a very important thing because your idea, if I tell you, well, there's microscopically reversible, macroscopically irreversible, the first idea one might have, that cannot be. But then you will understand, okay, well, physics is not only determined by the laws of motion. The laws of motion have a direction of time. It's also important to look at the initial conditions. And maybe there's some break of symmetry in the initial condition. That's in fact what Boltzmann ideas was. There's a break of symmetry in the initial condition. In some sense, the initial condition of most systems are very special, which has to do with the fact that the initial condition of our university seems to be a very special one. And this gives you the chance to have an error of time for the macroscopic world. And this is the very important thing, that this explanation relies on a very special initial condition. What does it mean to be a special initial condition? To make this a little bit more clear, let's assume the following. I'm not a religious person, but as I said, this will be important, this talk also for philosophy and maybe kind of religion, but I would like to give you just the picture, right? So you have God creating the world. So it doesn't need to be a God, no matter what creates the universe, but let's just have this picture. There's God, he creates the universe, and the way he creates the universe, he does it with a lot of randomness. And assume you have a universe which just consists of this big box with the two halves, and he throws a dice, and depending on the one side of the dice, there's an A, on the other side it's a W. That's also going back because I once gave this talk in German. R stands for eagle, which is on one side, it's an adler, the other for the heraldic symbol Wappen, but that's not important, so it's just a dice. And if it's an A, he puts the gas particle on the right side, the second particle he threw an A2, the third, she or he put it on the other side, and it goes on like this. Now, if you randomly create the positions like this, so deciding if it's on the left or on the right, more or less half of the particle will be there, more or less half the particle will be there. Now, if you want to do all particles on one side, as I did it when explaining that there is an error of time for the macroscopic world, well, the probability that this happens for n atoms is 2 to the minus n. For each atom, you have a 1/2 chance that it will be to the left or to the right. So it's 2 to the minus n. So this is a very special initial condition. Now, let me talk about this in more detail. So all this now has to do with order and chaos. Special system means, yeah, there's a lot of order in the system. All particles are put on one side. And the final system was very chaotic in the sense that there were particles here and there was the largest amount of chaos you could assume for the system. Now, talking about order and chaos is very important, and now I would like to give you a sentence which some of you might have heard in the past, which doesn't really make sense. And I would like to correct this sentence. You might have heard that physical systems approach the state of minimal energy. That doesn't make sense because the energy is always conserved of the total system. What is the right explanation? And we will make sense to it. What is really meant is the following. Physical systems approach the state of largest disorder. That's what happens. And that's not surprising. If you put order on the system and it starts to move and particles collide, this will create disorder, and physical systems approach the state of largest disorder. To prove this with mathematical rigor is really hard to do. And one of the hardest topics in kinetical gas theory. So this is a statement, and if you want to look more into details, this is very tough and something we might also want to discuss one day. But if you go to the simple picture I had, just to have a picture and an idea, some heuristic idea, that makes a lot of sense. You have this ordered system, all gas particles on one side, you let time evolve, and it starts to create more disorder in the sense that many particles are also on the left. Now the question is, what has disorder to do with energy? So sometimes this is the right statement. This seems to be empirically true, right? If you have a ball, you put it on a mountain, well, the ball goes down the mountain, right? To a state where the energy is less. And the point is, as you might know, the energy, all kinds of energy are transferred to temperature, to heat energy. And that's what disorder has to do. Temperature has to do with disorder. This is what I will explain in a second. Temperature, as we have learned before, is a form of energy, the kinetic energy of the particles flying around. So the right statement is this one. Physical systems approach the state of large disorder. And since increasing the temperature gives you a lot of disorder, well, systems tend to increase the temperature at the cost of other versions of the energy, right? So the ball likes to take over the kinetic energy, and by friction, this is transferred to temperature because that's how the full system gets the highest disorder. Now, why is temperature disorder? And now, I think most of you have had a probability class. So many of you visited my probability class some time ago, maybe not all of you, but at least you know that a measure for the temperature is the variance, right? So the variance measures the temperature. And now I would like to go to my sketch pad. Now, assume you look at the momentum of the system. Now, typically physical systems are described in phase space. So you take a space where you have the k vector, or the momentum. Yeah, some people like to call it k, some like to call it p. let me call it P, that's an decay anyways. So you have the momentum and you have the position X. So P is in R3, X is in R3 already, and it describes systems moving in the so-called phase space. You might know that phase space volume is conserved, so describing systems here, it's very easy. It makes a lot of sense because the probability measures are conserved. So it's clear how to talk about probabilities if you look at phase space. Also, this would be subject to another class to give you more details on that, but at least, you know, looking at the phase space, you can talk about order and disorder. Now the variance in P for a system which is where the center of mass is at rest is of course the expectation value of P squared minus the expectation value of P and squared. And if the system, the rest frame is at rest, this is just 0. So if you go to the rest frame of the system, you see that the variance in P is just given by the expectation value of P squared. And this, you see, P squared is the kinetic energy, right? Just up to a constant, to the constant division by 2m. But that's proportional to the kinetic energy. Sorry. Kinetic energy. Which means that this has to do with the temperature. Now, you start with something which is a measure of disorder. And if this increases, the variance increases, so the disorder increases. And you see that it's related to one part of the energy of the system, namely the kinetic energy of the atoms. And this explains why the temperature tends to increase of the system, because it gives disorder to the system, and why all the other forms of energy try to typically tend to the minimal value. And that gives also some kind of sense to this first sentence, which is not completely stupid, right? It has some empirical value, and this is some kind of explanation. And this has to do with the error of time, of course. Now, OHA, I didn't change the title here, sorry. I polished an old talk in German for a high school. So this means temperature and disorder of a system. Now, temperature is kinetic energy, as I just told you. High temperature is a high expectation of k squared, which is the variance of k, or the momentum variable. And you transform other forms of energy to temperature. That's what your systems do. Now, I would like to talk about something which now goes a little bit in the religious and philosophical direction. And I would like to talk about the wonder of life, which has a lot to do with all the things we have discussed now. Now, one question is our university ordered or chaotic? That's a very important question. And I have given now 2 answers to this question, which were completely opposing each other. If you go back to my gas laws, and I told you I want to describe and explain the gas laws the way Boltzmann did it. And there I said I have to assume that there is a high disorder in the system. Remember I said if all gas particles sit on each other and have the same velocity and hit all together at the same time the boundary, you will not have the empirical picture, which you will not see what you see in nature, that you have a more or less constant pressure on the boundaries of this gas. To have a constant pressure so that all these hits average out, so to say, I assume that there's high disorder. Now to explain the error of time, I need a lot of order in the system. And the question is now, is our universe ordered or disordered or chaotic? Now life is in a state of very high order. You know, if I do what I did before and I take all the atoms we are made of and throw them into the room we are sitting arbitrarily, we will not form a human, right? Probability is very small. So life is in a state of very high order. And to be able to continue living and create more life, we had to eat substance with high chemical energy. And you know, as we've just learned, all other forms of energy but temperature mean that there's a lot of order in the system, because you can take this chemical energy and exchange it to temperature, which gives more disorder to the system. And now, where does the chemical energy come from? Well, from the plants who created sugar and other substances. Well, they transferred the photons of high frequency to low frequency photons. Well, this is what plants do, right? There's sunlight with photons with comparably high frequency shining on the leaves. They transform it by photosynthesis to sugar, and also a little bit of heat. And heat means photons of low energy. And many of those, right? A few photons with high frequency are transferred to many, many, many low frequency photons and heat also. And altogether, they still produce some chemical energy in the sugar, of course, transforming water and carbon dioxide to sugar and oxygen. And at the same time, well, they take the order of the high frequency photons and transfer them to low frequency photons. That's only possible because in the center of our solar system, there is a sun which creates these high frequency photons. And if all the background was also had the same temperature as the sun, this wouldn't work. Just a side remark here. If you would live, there's a very nice idea telling you that it's our universe we have cannot have infinite volume with a certain constant density of stars. If that would be the case, all the sky, even at night, would be as bright as the sun, because in any direction, the probability that if you go far enough, that you will hit one or another star is very close to 1. And in such a system, also plants would not work the way they do it. So here it's very important that there's a sun and the most part of the sky is dark, so to say. And this is a very important feature here. So the story goes back always a step backwards, and each step backwards gives you a system of higher order, if in fact. And the question is, where does the high order come from the very beginning? And this is a very important question that has to be asked. And again, as I said, there's this kind of a strange thing. The very high order, we have to assume very high order for the initial system, such that we can have this behavior here to describe life, which is an empirical fact. But then the same high disorder to describe the gas laws. And what is now the situation? Is our universe ordered or chaotic? And that's something that has to be answered. Now there's some possible explanations for this high order of the initial system, or where the high order comes from. The first one, which was given by colleagues of Boltzmann already, and there you see how smart Boltzmann was. All these discussions happened already when he was still alive. And honestly, there's not many new insights in these fundamental questions until he died, but one of the last steps which I would like to explain you later. Now there was this fluctuation hypothesis which does not work. And this is something I will explain you on the next slides. Another explanation could be some kind of creator, some kind of God, or some kind of mechanism, or might it be intelligent or not, which has leads to a high order in the system for some reason. Another idea is that there is a natural constant with a time direction, that also our microscopic world has a time already. You might know the quote of Einstein, who once said his biggest mistake was something related to his cosmological constant. And there's the debate until today if this cosmological constant is time dependent or not. Now, if you have a natural constant which is time dependent, it's not so surprising that you get a direction of time for the macroscopic world. And in fact, you get so much order that it can explain the creation of life. I would like to give you an example. Let's assume a very simple model of a universe, not gravitation in the Einstein way, no quantum mechanics, but a box. Assume our universe is in a box. You have Newtonian equations of motion for many particles in this box, but you have gravity. And the system is such that the gravitation constant is 0 initially, and then it goes up. One important insight in kinetic gas theory is the insight that what it means to be typical or ordered always has a little bit to do with the equations of motions. And now if you start with a system where there's no gravity, you might say, well, the highest disorder or the most chaotic system is where the density of the system is more or less constant. Now, if you start to turn on now a gravitational force and you have a constant density at the beginning, these many particles will start to cluster. They really will form stars the way you have learned how stars are being formed. You have some kind of a gas, let's say hydrogen, and this starts to collapse, starts to rotate, radiate away some of this energy, and so on. Well, why does this happen? Well, because the gravitational force gives you energy, right, to the system. This energy is transferred to temperature. And now there's two ways, of course. It somewhat gives you more chaos to have a constant density in space, but on the other hand, heating up the system helps too to produce more chaos, as we have just learned. And there's a balance between those two things. And the balance is not such that you have a constant energy. No, the balance is that you have formation of stars. And now if you have a system where stars are formed, that explains the creation of life, right? Because the stars will radiate high frequency photons. You have plants which are formed, which consume these photons, and so on and so on. Now, if a natural constant has a time direction, and for the simple model, just from 0 to a certain time, the gravitational constant is changed, this would explain all these things. But that's, of course, less puzzling. Just a side remark, and another side remark, sometimes one hears that quantum mechanics has a time direction already because of the collapse. I don't like this argument for many reasons. First of all, the description of quantum mechanics one typically learns is something I think is a big mistake in science. The usual approach to quantum mechanics, where you have this collapse and where you have this interaction with macroscopic objects, measurement devices already in the fundamental formulation of your theory, is wrong. There's other options how these things can be done with true microscopic formulas where there's no collapse, where there's no interaction with microscopic devices, which is a true fundamental theory and not half fundamental, half effective, and things like that. And all these descriptions, they are reversible in time. And I think that this is not a good explanation. But that's also another topic, and I can't say too much in this talk today. Now, all these points here were present already at Boltzmann times and discussed. And as I said, I would like to talk about the fluctuation hypothesis in a moment. So now it's almost 1 hour, so I have to speed up a little bit. But there's a very new insight, and this is something I would like to discuss with you, that there are systems without equilibrium state. And there it might really be possible that you have a microscopic reversible but macroscopic irreversible system. This is something I will do on my final slide, and this is a very new idea. Just a few words on the fluctuation hypothesis. Well, the idea goes back to colleagues of Boltzmann who said, well, now, how can you explain that there's at the same time high order and disorder? And the idea was the following, that the order in our universe is just a random fluctuation in the system. And that's the anthropic principle. So the boundary condition, there has to be enough order to form a physicist. So let me explain that in more detail. Assume our universe is described by a god throwing dice. And he throws dice all the time. So you have 1, 3, 5, 6, all kind of chaotic orders of numbers between 1 and 6. Now, to form something which has enough order that a human brain can be created out of it, you need, let's say just an example, 1,000,000 sixes, one after the other. You know that this is not very probable, but if you throw the dice long enough, the probability is very large that eventually this will happen. You have to wait an extremely long time, but eventually it will happen. And when this happens, you have enough order to form a brain. Now you might say, well, this is not a very probable situation, but you must, of course, it should be clear to us that the fact that we discuss is related to the boundary condition that we exist. Now, if you say, okay, there has to be a lot of order to make sure that there are humans and physicists who can describe physics. So the boundary condition is that, yeah, the system had to wait until there was so much order in the system. It seems to make a lot of sense. And now the idea was, okay, there's some completely disordered system, chaotic system, there's some kind of fluctuation, nothing happens. And eventually the fluctuation is so large that there's so much order in the system that there's life. And this would describe why most parts of our universe are chaotic and why there's on the one hand chaos, but on the other hand, there are some physicists doing science. Well, on the first view, this seems to make sense, but Boltzmann directly refuted and proved this argument to be wrong. Now, first of all, the disorder in our universe, the order in our universe is far too large, not the disorder. The order is far too large. And one could ask, if one agrees with this hypothesis, the following question: what is the conditional probability to find a second physicist next to the first one? Now, if you assume this to be true, so the anthropic principle says, of course, there has to be a human, anthropos human, there has to be a human in your universe, otherwise there was nobody who can do physics. Now, if you assume that the fluctuation, or look at all kinds of fluctuations, the number of fluctuations which create just one human is a billion times higher than the number of fluctuations which form two humans. And of course, there are at least two humans in our universe, even many more. Or another argument, if you would now, assuming that this is right, and find a new island somewhere in the ocean, you would assume that this island, everything is completely chaotic, because you don't need order in this island to describe what you have seen in your past, to describe physics, to describe your mere existence. But you would also expect on this island that there's order, that there's plants and animals. So this fluctuation hypothesis does not work, which Boltzmann already found out. Now this is the last point I would like to discuss. Modern insight. The idea goes back to Jean Carroll. And the idea is that there might be systems without an equilibrium state. What does it mean to have an equilibrium state? Well, this is, let's say, a system which has some kind of, which heats up and there's some kind of a final state where the story is over. For example, in this box of, the two boxes of this gas, where half the particles are on the left and half are on the right. And if this system goes on, not very much will happen. But if you have a system without such an equilibrium, the entropy might grow without limitation for most initial states. That was the finding of Jean Carroll. And I would like to give you a system which might have exactly this behavior. Assume, again, you have one box, maybe a torus. The boundary conditions, if you have some walls there, or if you leave the box on the right, you come back on the left, that doesn't matter at all. Just some kind of a box or torus. Many particles. Assume you have Newtonian gravitation with a full singularity. Now what happens with this system? No matter how the system starts, the temperature can always grow. Because particles can get closer and closer and heat up even more. Now you would start with these many particles, they fly around. Eventually two particles will become very close, and another particle might also come close to them, and they may use the potential energy to get closer and kick this other particle away. So some of their potential energy is transferred to kinetic energy. But if you have a full singularity, you know that the potential energy you can give to these particles is not bounded, can be infinitely high. So later it might happen that another particle gets, you have something like two particles flying around of each other, like a two-star system, so to say. If you wait longer, another particle might hit those two and bring them closer together and get more kinetic energy and so on. And there's no limitation for the temperature. And since there's no limitation for the temperature, there's no limitation for the disorder you can give to the system. And if a system starts to create more and more disorder, the idea is, no matter where you start, for any initial state, you have the possibility to create more disorder. And this is what will happen. And then you have a direction of time again, namely from small disorder to high disorder without an initial state. Now this idea, as I said, goes back to Jean Carroll. This is just, the idea is not much more than what I explained, you know, it's very heuristic. I have some DFT project at the moment. This is like an NSF grant together with a PhD student to find a very simplified model of this system. Many particles, so that it should be many particles in a box with gravitation. Then this is the idea we had together. Jean Carroll described other systems, but this is something we think might describe this behavior already. And what we are trying to do now is to find a system which does not be close to the system that really describes our universe. You might say, okay, that's a made up system because Newtonian, you should do quantum and not Newtonian gravitation, but relativity and all these things. But if you have understood the talk is not only about our universe, it's about principle question. Is it in principle possible to have equations of motions for many particle systems, also in kind of made up model universes, which showed these kinds of behaviors that you have a direction of time for the macroscopic world. So it's more a matter of principles. The question, is it possible? And if you want to prove a statement, yes, it is possible. It's nice to give an example. So the system can be made up as much as you like. It should just have the right features. And we are now trying to make a system where we really can give a mathematical proof that for these systems, you have a macroscopic error of time and that they are microscopic irreversible. Microscopic reversible. Now this is my final slide. I think the time was a little bit longer than expected, but still I'm open to all kinds of questions, all kinds of suggestions for further talks, workshops, seminars, whatever, on all kinds of topics we have touched today. And I would like to give the word to you now.
So just to make sure, so basically when we talked about the system was like a box and like a little hole where like particles can go from one half to another, we said that there is an arrow of time because like it's much likely that they all would spread out, then they would all go to one half. But like
Exactly.
But there's still like a little probability that this would happen, and they all would just like go and gather in like one half, and maybe like after like, I don't know, centuries or whatever, right?
Yes, that's a very good, that's a very smart remark, yeah. Always very smart remarks from Annika, yeah. Very smart remark, Annika. Now, let's go back. I have the system here, you can still see it, right? Now, if you look at the system from the macroscopic point of view, assume you would really have these two boxes and there's gas in this half of the box and no gas here. You could have some kind of machine here which produces electricity, for example, right? You have some wind going through the hole now, and you can have some machine which produces electricity, and you have one direction of time. And eventually the system will like this. And from the empirics, you know, if you really have this box like this, that the gas density on the left and on the right will be more or less constant. And if you do experiments, you know it will not change so much in time. Now you're completely right. There will be fluctuations. Let's say you have 10 to the 23 particles in the system. From time to time, typically the fluctuations will be the square root of that. So let's say 10 to the 10, something like this, right? And if you wait enough, like with the throwing sixes, it will happen that the fluctuations get larger, that you really have some, maybe this difference in the density, which you really can measure with some measurement device. And if you wait even longer, you will see that maybe all particles, and eventually, if you wait very long, all particles will be on the right. Now, the point is that the time scales when this happens are so long that you will never see it appearing. Now, there's calculations for very simple systems of gas particles where you have two boxes, and typically the time scales are many, many powers of the lifetime of a universe. If you have already some gas with a certain density, it's 10 to the something like the lifetime of a universe. If the number of particles is sufficiently large to really call it a gas and it's just a bunch of particles. And of course, there's a boundary region where you're somewhat in between, where some strange things happen, and it's still many particles, something like a gas, but that's the fact. This is something which has been, of course, discussed. This is called Poincaré recurrence, by the way, that if you start with a system, there will be a time where the system recurs to its initial state. That's called, that this happens was formulated by Poincaré, I guess, for the first time, and it's called Poincaré recurrence, and Poincaré recurrence is just a fact. But it takes so long that we don't see it. And of course, we want to describe the physics of our universe. And I would like to describe what happens in, let's say, 1 billion years or 5 billion years, because our universe, the lifetime, our universe so far is roughly 5 or 7 billion years, I don't know, right? And if you say, okay, your time frame is 7 billion years, and you would explain physics here, then the probability that you go back to this initial state is so small that you can forget about it.
So it's kind of like the time arrow exists for us because we live so short. But like, say, if there's like an immortal being for whom those time scales aren't that big, like for those immortal creatures, like the arrow of time wouldn't exist?
That's a good question, and this is something we can't answer, because as I told you, there's different possible explanation. Now, if you assume there's a system, and let's assume the following. There was a God, for example, and this God wanted that there's life and created a very special initial state because he wanted that there's humans. And then after all humans are gone, there's the so-called heat death, that everything has heated up to the maximum possible temperature. All other forms of energy are transferred to temperature, and there's complete chaos, and the system is completely dead and nothing's going on anymore. And being which lives forever might say, okay, for a very short amount of time at the beginning, there was something going on, but most of the time, the universe is just dead. And there comes the fluctuations and maybe large fluctuations. And if he waits even longer, maybe recurrence to the initial state, and everything goes on from the very beginning. But most of the time, only very ridiculous small time intervals, there's something like a little bit of a life. And most of the time, it's completely boring and chaotic. So this was the idea at Boltzmann times. Now, if you look at the final argument which I gave, if there's no equilibrium state, if the system can heat up and heat up and heat up and heat up, and it doesn't stop, such a being would see a system which heats up and heats up, heats up, and never stops, and has an arrow of time, maybe forever, right? This is something we want to find out. And we want, as I said, our statement is not the statement about our universe, because there's too many things which are unknown for our universe, and it's too complicated. Our research is more a principle research. Is it in principle possible to have a dynamical system of many particles where you really have this behavior that it heats up and heats up and heats up forever, and where such a being which you described really sees an arrow of time forever? Now, going back to this, he wouldn't see an arrow of time. You would, this thing, because it would also go backwards, right? The fluctuation, it's not an arrow of time. You would have life, but you would also see strange things happen, because when the fluctuation starts to form, when it comes to chaos to order, strange things will happen, and things will happen like the glass going backwards, right? You have a chaos and it forms a glass, for example. Well, then what I shown you in the movie will happen, and things like this. And for this supernatural being, we will not say there's an error of time. We will just say, well, there's chaos, and from time to time, strange things happen.
Order.
And order starts to form from time to time in a very strange way, just like in the movie with the glass. And then the glass again breaks. After a while, you know, when the fluctuation is formed, you create the glass. Then when the fluctuation vanishes again, which is the more natural process, the glass breaks again, and he will see many strange things, but not really an error of time.
But then, does it all depend on our definition of order?
Again, a very smart question, Annika. Yes and no. First of all, yes, it depends all on our definition of order. If you redefine order, it go very differently. But we're not just defining order just for fun in a way we want to. But the notion of order has very lot to do with the dynamics of the system. And that's a very important question. So typically what one does in the statistical theory of gases, you look at the equations of motion of your system. You say, okay, I have a Newtonian universe, for example. Given this equation of motions, you have now to find a definition, what is order, what is disorder. And this has to do with a probability measure. You have to find a probability measure for the system. And this probability measure says, well, things which have small probability is high order. Things which have probability close to 1 is high disorder. The question is, what is the right probability in the measure? Now, the right probability measure is usually the one which is conserved in time. Because if your microscopic system has an error of time, is reversible, then you will say, okay, the probability measure should not change in time. So it's not really that we can freely choose the probability measure. Given by the physical laws, there are certain probability measures which make sense to describe the system, because then having probability at time 0 and at time 1 is the same thing, right? If there's a deterministic things going on, and I say, okay, the probability that I hold my phone here is a certain probability, and if I let it go, the probability that it will be there in 0.1 seconds has, of course, the same probability. So you have to find a probability measure which pays respect to that with the systems. So the answer is yes, it very much depends on the probability measure, and so to say on our definition of order and disorder. But finally, it's not our choice just to define some probability measure. There's some boundary condition on which measures make sense. And so finally, there's no choice. And since there's no choice, there's also no dependence on how to define it. If there's only one way to define it, then this vanishes. And this is very important. For example, if you go back to the system I described, if you have a system where there's no gravity, the most ordered state is the one where the density is constant in space. If you look at the system where there's gravity, you will have stars. On the first view, this might look strange. You still see my screen, right? But if you go to ordinary space, if you just go to space, you will have constant density. It's the high order. If you have gravitation, we will have stars, right? But if you look at the system on phase space, so if you have a space where you have the momentum and the x, this might be something, this is maybe the highest momentum for the total system possible. This might be like this. And here it's like that for certain positions where you have strong clusters, certain positions where you have clusters, you have more possibilities to have high energy. So the system on phase space more looks like this. These are the points where there's many stars. Probability to have clusters. If you forget about the p variable, and just look at the x's, here's much more probability, right? This is now the probability measure. So it's more probable to have stars than to have no stars. Because when you have stars, you get potential energy. This can be transformed to kinetic energy. So higher kinetic energies are possible, because this here, of course, this boundary is always the maximum of the square root of the kinetic energy, right? Because more momentum is not possible. And if the kinetic energy depends on the spatial formation, you will see it naturally looks like this. So if you go to phase space, there's so much of a difference, right? You just take the boundary conditions and look at all possible states which have, let's say, a kinetic energy which is smaller than a certain value. And then here you have a constant density, here you have clusters and stars. And there you see that it depends a little bit on the system you're looking at, on the dynamics and all these kinds of things, how disorder and order looks like in such systems. And therefore, it's clear that if you have gravitation, the highest disorder is not constant density, the highest disorder is really stars in the system.
So, Professor, you just said you just mentioned heat death. Do you think after heat death happens, everything will just start over again, or what happens? What would likely happen after heat death? Assuming there is an after.
Yeah. So if you really assume there's a system with this kind of equilibrium state, here's time, here's the entropy or the disorder. You don't have to have a mathematical description for it. So let's say this is just the disorder. And assume you have a system which has a so-called equilibrium state. An equilibrium state is a state of highest disorder, that it's not possible to give any more disorder to the system because all other forms of energy has been transferred to temperature already, right? So if you have such a state of disorder, your system has this boundary and will stay below. Now, if you assume God created a universe here, now the disorder grows, and then it will be here, and then it will stay. But from time to time, there will be kind of fluctuations, small fluctuations, ones, and even fluctuations if the time is ridiculously high. You know, these time frames are ridiculously high, such that you go down again, right? And you would have, during this time interval, if you look at the universe, it will look completely ridiculous, right? From the core, things are formed. This is where it really happens, that you have all kinds of splatters and they form a glass here in this time interval, and not just one, so much that all our universe has a lot of order. And now if this happens, this is a fluctuation. As Annika pointed out, this will happen. The time frame is so long that it's completely crazy, but eventually it will happen. And then if you're here, everything starts anew and you will have life appearing. Now you would say, well, could describe, that's the fluctuation hypothesis. This could describe our life, because here there's nobody, here there's nobody, and here on this point of time, there's you discussing physics, and here there's no you're discussing physics, so there's also no physics book, and nobody cares about it. And since you are here to discuss physics, therefore that's the anthropic principle. You see this universe and have an explanation for the growth of time. But what we've used the hypothesis is, well, there's an UA2 here, and there's you and no Peter and no Annika and no other human. And in fact, what Boltzmann says, it's not you as a human, it's just your brain here. And to form your brain, and not your whole body is smaller. And you will have these fluctuations. And there's a million fluctuations where there's just your brain, before there's one which is so deep that there's even the full person, and even 10 to the many huge numbers more, until there's a second person, or the universe as we see it. So this is something of the fluctuations or the smallness of entropy our universe has. Well, on the picture, it's just, you know, it's just a graph. But that's so ridiculously or so incredibly small, it's almost indisputable. And this is something which happens. So before you see, for chance, a universe like ours appear, you have the brain of a person, and this brain just does physics and nothing else, and that already a zillion times. But to answer your question, in principle, yes, if you wait until the fluctuation is so deep, that it's as deep as our initial state of the universe, everything will start again. And there will be zillions of events in between where you have just a universe where there's one island where there's no plants, but on all the others, and you will see many, many strange things. And if I say, okay, there's one fluctuation where our universe looks all like ours, but in Australia, there's complete chaos and no animal and plants. This will be still ridiculously small and will not contradict to anything we see. But the fact that we know how Australia looks like, it's assumed James Cook never existed and we have never found Australia, we would still believe it's wrong. Although there's the probability for this, or the number of fluctuations which are like that, is a zillion times higher than this fluctuation where there's order and plants and animals in Australia. So we don't think that this is the right explanation, right? And honestly, I'm quite happy now that there's these new ideas of John Carroll, which there might be something to it, but that's something that has to be found out. So many physicists really believe that there is some external reason which has nothing to do, right? There is always in physics, there's a boundary condition, and there is a boundary condition which caused our initial state to be very, very, very ordered. Whether you call this God, well, whether this was a being, a supernatural being, or whether this is just some physical law which comes from somewhere else, this is not so important for us. Maybe for people who are religious or philosophers, this might be very important, this question, right? But I'm not a religious person, to be honest. So, but still, you know, the word God does not only refer here to a supernatural being which has emotions and consciousness. It means something which is outside, a little bit outside physics maybe, or which causes the initial state to be special or whatever. And that's an explanation, however you like it. But you see that this is a topic which is very interesting to philosophers. And of course, finding out whether this last possibility really exists, which is still actual debate, would be interesting, right, in this discussion.
Yeah.
So if a system doesn't have an equilibrium state, it basically means that we can like forever take some other energy, convert it to temperature, and just go and go and go on. But like then it means that we have basically infinite amount of energy in the universe.
Yes, exactly. And that's the kind, if you really have Newtonian gravitation with the full singularity, you have an infinite amount of potential energy which you can extract out of the system. So think about 2 point particles, you bring them closer and closer and closer and closer, and the potential energy you create by bringing them closer has no boundary. That can go to infinity.
Yeah, but in reality, there are no such things as point particles. Everything,
absolutely. Absolutely, yeah, I completely agree. That's some kind of a problem. So our research is saying, okay, we first start with a system which is completely made up. We have point particles, and see if in principle there is dynamic a system where behavior like that appears. And then the next question is, what about our universe? Of course, there is no point particles, but there's other effects. There's Einstein gravitation, which has different features. There's event horizons. There's all kinds of different things going on. And the question is, are there maybe other effects which can lead to that? And finally, one needs some source of an infinite energy. And it's doubtful whether this exists, I agree. I agree. So even if our research here is positive and we say there are systems, the question is whether this can be transported to our universe is very questionable. And it might be that we say, okay, yes, there's a principal possibility, but for our universe, there is an equilibrium state that we don't have a source of energy which is infinite. And then we have to go back to those two possible explanations where this doesn't work. So either there was a very special initial state, or our universe was irreversible from the very beginning, because there's a constant with time direction. Both is in principle possible. Okay, I see Annika has to leave soon. And now, if you like, I can do the following. I give you a few. There was the question on Vlasov. This could be a little bit more technical. So we can either, when I come to DKU, I hope that this will be possible sooner than later. I can give a talk about it, or we can discuss together in a smaller group. Just let us see, and I can do something which is more technical, if you like, because the talk today was more conventional. For the Vlasov, I can really show you the math, how to derive a Vlasov equation, which is kind of nice, and I would like to do that. I'm not sure how many students will be interested in that, but if there's only 3 or 4, that's completely fine. And we can do it a little bit less like a seminar talk, more like a discussion, right? That's fine. And we can do that when I come to DKU anytime. And
Yay, that would be great.
yes, good. And if it still takes a long time to be able to come to China, I think from Europe it might be easier than from the US, because here the corona cases are decreasing. In Germany, the number of cases is comparably small. So maybe there's the chance to visit China next year. Let's see.
Or if we don't, we can just continue doing online stuff.
Yeah, of course. No, I can give the Vlasov talk also online and try to give you more details and have seminar. It was a pleasure to meet you, really. I miss you a lot, honestly. I enjoyed being in Kunshan so much, and it was, thanks a lot for the invitation again. That's really nice.
When you come to Kunshan next time, we'll take you to Bubble Tea Place.
Yes, very good. No, I like this idea. Yes, good. To the Bubble Tea Place. Good.
Should be great.
Okay. Yeah, you must also miss the other students, right?
Yeah.
Okay.
But we see them in online classes.
Yeah, okay, yeah, but that's not the same, right? So then, guys, enjoy your afternoon.
Yeah. Enjoy your afternoon too. Can you send me the link to the cloud after that so I can like download it and stuff?
Who has the link to the cloud?
I think you're recording right now, right? So after we finish the conference, you would have a video recording.
I get it by email or so. I see. Yes.
Oh, okay. Great.
Yes.
Okay.
Okay. Bye, everybody.
Thank you so much. Bye.
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 Thank you.
Bye.
Thank you.
You're welcome.